Okay, could you guys see my screen?
Yes.
Okay, is it big enough?
You want to go full screen or not?
Let me check how to do full screen.
How about, yeah, that one. Full screen mode.
Okay.
Yeah.
Okay, is it now full screen?
Yeah.
Okay, okay, let's start. So, good afternoon to my supervisor and Dr. Ma. And today I'm gonna talk about a very new topic on geometric Langlands. That is geometric Langlands conjecture. Particularly, I will focus on the construction of the Langlands functor based on the idea from Yaskori and Sam Rensky. So this paper, what I have done is like review what are the major tools being used by Dennis and Sam on the construction of the landing functors. Of course, there are many technicalities in this topic, so I may be wrong in what I have shared maybe later. And I will skip some of the technicalities, but the main word is like to bridge the gap between the reader and the broader framework of the geometry linear conjecture, and introduce some essential concepts that being used by the frontiers in algebraic geometry. Particularly here, I mean the derived algebraic geometry, which we will see later, and of course the infinity categories. And in this topic, I think even all of the categories that we discuss will be will be as infinity categories. And particularly, we will see how they define the automorphic and spectral sites of the GLC. And if possible, I will also present the simpler case where they also show that what if the group is a torus. So let's begin. So before we get into our derived algebraic geometry, so I will now recap some necessary notions in classical algebraic geometry. The first one is the Noetherian screen. Particularly, this Noetherian screen is useful for describing the scheme of finite type, which is the following definition. The Noetherian scheme is defined as if a scheme can be covered by finite limited affine open scheme, then we call it a Noetherian. So here we will take this AI, and then we will say a scheme of finite type is finite type over a ring B if S has finite covering such that this AI is finally generated algebras over B. Next, and to describe how we call a DRAM preset, which I will introduce later, we require the definition of a reduced scheme. So if a affine scheme X is a spectrum of a ring R, if R is a reduced ring, meaning it has no non-zero nilpotent elements. Now, note that this is an affine scheme, and generally a scheme is defined as a reduced scheme is defined as if it can be covered by reduced affine schemes. So this is our usual definition of a pre-steps in modern algebraic geometry. So a modern pre-step is like there is a functor. Generally, a pre-step is a functor between one categories, and it satisfies the following condition. Particularly, it requires the pullbacks to be existed, and this is a universal property for the pullbacks. And as I mentioned before, that in this context, our GLC is focusing on derived algebraic geometry. So we not only looking at the usual pre-step, we're particularly looking at the derived category of pre-step, meaning our preset is now derived in the sense that defined as follow. Before we get into the derived preset, we will look at this category. So they actually consider the stable symmetric monodal category of that, and its full monodal subcategory less than equal to, or equal to 0. This particularly the T structure, if you recall. And by a connected community algebra, DG algebra of K, we mean a community algebra object in bed less than or equal to 0. Connected here means that the object is actually live in the less than or equal 0 side in the sense of our usual T structure. And the collection of this algebra and the multiplication form an infinity category is defined as follow. So what is our main target, which is our derived preset? So our derived preset is actually a funder. And this fund is actually means we consider all the collections of funders between these two spaces. And this SPC is actually denote the infinity category of spaces, or in their words, they mean the infinity group points. Our user group point is defined as a our one group point is defined as the category of which the morphism is an isomorphism. So the infinity here is like not only you consider the one morphism, but you also consider one morphism, two morphism, three morphism, up to infinity morphism. So next. So after we define the direct preset and how they actually can produce a new source of preset, yes, especially by this, they call the mapping space or mapping preset. The mapping preset is defined as follows. Suppose here we have Z, X in the preset, meaning this Z and X is actually the derived preset, and this X is actually the object from this category. And once you put into this mapping preset, it actually produce a new preset, and it's defined as the fiber product between X and this X. This actually is very important for us to define the main ingredients for our GLC, which we will see later. And as I mentioned, the DRAM preset is actually defined as follow. So the DRAM preset is actually the preset, is the usual preset, but it carries our usual scheme. And S here is not this CL is stand for classical, and red is reduced, which I mentioned just now, the reduced scheme. And this classical means our usual scheme, in the sense of usual scheme, not the derived scheme. So now we will see how actually they use this definition to produce one of the main ingredients in our GLC, which is our moduli stacks of G bundles. And actually they define the boundary as follows: the maps between the X to the point over G. And this construction is actually they involve of quite a lot of technicalities, and they actually prove even in one paper about the compact. I think it's about the compact generation of the modules. So one might look for this detail in that paper. But so this recorded boundary is actually what we want in our, let me see, in this, we want to map this boundary assigned to this D mod. But before that, we'll introduce what is a D module. So D modules is very classical. I think it's even mentioned, quite frequently mentioned in this few months because of that Kashiwara getting the prize on particle on this theory. The modules is basically study actually in connection with the Riemann-Hilbert correspondence, which is also being used in GLC, particularly in the setting of in the betting setting. But in our case, I will only focus on the DRAM setting, so this won't be touched very frequently. But and also, actually, D modules you can think it as it consists of the data of the system of linear differential equations. And what is amazing is about like actually through this Riemann-Hilbert correspondence, one can see that actually there is an equivalence between the linear linear differential equations to its solution space, particularly the home space between the kernel and something like that. But I won't touch that about that topic. But it's quite amazing for this Riemann-Hilbert correspondence and how it's being used in. But it's how I think the module is like the connection between the ordinary linear differential equation with its solution space. So how is defined in our context, in our GLC context? So when we're trying to assign a preset into a D mode, then it's actually defined as a quasi-coherent of this just the DRAM preset. And this is how they define, but actually there's pass-through of a lot of quite technical.
I like to ask a question. What is Y?
This is a normal preset because if in this definition we take Y from the preset, so this preset is actually the derived preset from in this is a derived preset. Okay.
Y is a preset.
Yeah.
Okay, then what is can you show me the next page? What is
Next
D
page.
mod Y? D mod Y are all D modules on the preset?
Yes. The say is like assign a preset on a D module.
Okay, so this is a definition.
Yeah, they say there is a definition, but of course they actually go through a lot of construction. So yeah.
So let's see if Y is just a scheme. So it's
Y
also
is,
Y is just a fine scheme. What is the D mod? Y.
Y is a fine scheme. Y is a D mod.
Just A1. Y is A1. What is D mod A1?
Y is the let me think.
What is Q cohom? Q cohom? Y the wrong. What is Y the wrong? Okay, so first of all, if Y is A1, what is Y the wrong?
Y, okay, I know the question. You mean if Y is A1, what is Y? What is this A1 DRAM, right?
Yes.
But your A1 is a ring, right?
No, A1 is the scheme.
A1 is scheme. Okay.
A1, it's
You mean
the border. Yeah. It's just a spec of CX, the polynomial ring.
R5 one space.
Yeah.
Is R5 one space pre-state or not?
I don't think so.
A fine one is a scheme. Scheme must be a stack. Stack is a generalization of a scheme, right?
Yeah. I know. Yeah, I know. Sorry, so I couldn't figure it out for now, but could I continue first?
Sure.
Okay. So next, okay, so basically this demod and this bound, our goal is like to assign our bound inside this D module. So this is what you call this the automorphic side of our GLC. So now we look at our structural side of our GLC. The one of the ingredients is the local system. So here is why we use the definition of one finite type. So the preset of G-local system is defined as follows, which is also using the mapping stack. And here you also use our DRAM preset. So with this in mind, we need to also assign some our spectral side of GLC is this, and we need to assign our LS local system into this category. And so given a scheme of almost finite type, so our induced coherent shift, the category of induced coherent shift is defined to be the induced completion of another subcategory, which is the quasi-coherent shift. And this subcategory is particular our regular coherent shift that consists of objects that are cohomologically bounded, and all of whose cohomologies are coherent shift on the classical scheme underlying X. So, why do we consider such categories? So there are various reasons for that, and one of the reasons that I get is if we consider the map between the preset X and Y, and which is a closed embedding, and we have the user direct image bundle as follows. And there's another adjoint theorem says that this above bundle emits a right adjoint and is denoted as follows. But the conclusion is why we consider induced coherent shift is because the F star doesn't necessarily preserve compactness. So why we need compactness is basically the property of the Langlands functor. So we need to make sure our Langlands functor preserves the compactness. But in this case, this doesn't necessarily preserve our compactness. So we need to resolve this issue. So we need such notion of induced completion. So yeah. So also all of these categories that we define is actually infinity categories. So one of the key reasons they use infinity categories is they can actually build a category through gluing via limits, and this limit is they going through all the our usual affine schemes, and then it mapping into the preset. And for example, the quasi-coherent shift that we've seen just now is actually constructed by gluing those categories of affine open covers of X. And this is actually extends to our D modules, just like how I defined previously in this. But in this case, our preset is a DRAM preset. Okay, so moreover, not only we look at the usual infinity categories, we also look at particular what they call the stable infinity categories. And one of the significance of doing stable infinity categories is they can look at they support the notion of T structures, which basically they consider the whole. You can think of it, look at the cohomology group like the greater or equal to 0 and the less than or equal to 0 side, and the core what they call is the like the star, and the heart is like the intersection between those greater or the cohomology group of the greater of or equal to 0 or and less than or equal to 0. So the infinity category of such category actually possesses a very important structure that is called the symmetry modular structure. And this structure is actually very important for preserve some certain properties of the Langlands functor. So we will first look at the definition of stable infinity categories. So the stable category is defined as if it contains all the fiber products and the push-outs, and the map from the initial object to the final object is an isomorphism, and if the following diagram is a pullback square, if only if it is a pull out square. So what is a symmetric modular structure? So basically, it's like it's a category with a structure such that when we take two objects from the categories, and then it's actually like a tensor product over certain field. But in this case, in GLC, they actually take it to be over the vec category. So this is our GLC in the DRAM setting. So basically, they wish to prove this is an equivalence, but since I only consider on the construction of Langlands functor, so I will skip this part. But I will only show this. There exists such functor between these two objects. So the automorphic side is correspond to the half twisted D modules on boundary, and the spectral side is correspond to the induced coherent shift with nilpotent singular support. This nu is stands for the nilpotent support, and is somehow related to the Artin state and stuff, if you really intend to know about it. And actually, to show there's a such functor is actually equivalent to show there exists a functor which characterized by the following properties. And this side I will define it later. And the first step they do is to study the object in the D module. And the D module is defined, the object in this D module is named to be the vacuum Poincare shift, and is defined as follows. And to unravel all this definition is actually, for me, it's quite difficult. So I only pick on some of the main points. So they actually go through a lot of papers to unravel this object, and basically this exponential is the exponential D module, and this chi star is actually a pullback for chi, and it's live in this thing. But the main point is with this Poincare shift, and actually they actually can define a quasi-coherent with this local system linear functor to this, and its definition is as follows. They define this functor, and then they look at the right adjoint of this functor, how we call the cos Langlands functor, And the target is to upgrade this cost funder to our actual Langlands funder to composition with this funder. Okay, so and there's the claim that to show this theorem, to show this theorem is equivalent. Sorry, I mean to show this theorem is equivalent to show the above two lemmas, and with that, they actually combine this result with our this side new and the zero set, and they can obtain the Langlands funder. But yeah, I mean, if we look at the case when the G here, the G here is T, which is a torus, then there's a Fourier-Mukai equivalence. They use the Fourier-Mukai equivalence, and then they enhance this to this funder. And actually, you can think there's a commutative diagram, and we can see that actually this enhanced Fourier-Mukai funder is corresponds to our Langlands, the cost Langlands version funder in our general case. So we can to get the Langlands funder out of this is very simple. It's just simply setting our the cost version of Langlands funder to be our Langlands funder. So yeah, that's basically what I have done so far in my project. Yeah, Dr. Ma, you can continue if you have any question.
Can you define what is bounty?
Bounty. Meaning there is a
bounty. What are the elements in bounty?
Meaning is a moduli state of torus funder, right?
Can you give me the definition?
Oh, you mean if this is a torus, right?
Yeah. So what is bounty? What is X here?
Oh, yeah. Wait.
What are the objects in bounty? So X is the arbitrary scheme, right? Let's say X is a point. What are the elements in bounty point? Let's say T is suppose T is GM. Okay, G is GM. X is a point. What is the bounty point? By definition, it's a map from the pointer to point quotient GM, right? So this is a set.
Pardon, may I know what is GM?
GM is the simplest torus multiplicative group.
Okay.
C cross, say the C point of GM is a C cross, right?
Okay.
You have GA, you have GM. Okay, what is a torus? Could you give me an example of a torus?
One of the simplest that I can think of is the complex number space of quotient out the zero set at the zero.
Delete the zero, right?
Yeah.
Yes, this is the GM.
Yeah.
This is the GM. Yeah. Okay. So what is the bound GM x where x is a point? This is a set. So what is this set?
Okay, I think the time is up. Maybe so you can
maybe
write a solution for Jiajing later.
Yeah.
Okay.
Yeah, there's some unanswered question, right? Maybe you can write the solution for him, and then you can
Okay, sure,
discuss
sure.
through email. Okay, thank you, Jiajing,
Okay,
and
thank you. Bye bye.
Okay, thank you.
So Jiajun is your student here?